So we just got done realizing the importance of that crazy little lambda thing, and we just learned about eigenvectors as well as eigenvalues. And so what we're going to do is kind of take a little bit of a pause and say, so imagine we have some coefficient matrix. We should be able to prove whether or not something is an eigenvector. And if it is, what's its eigenvalue? So here's a vector. We can call this vector v. And the question is that an eigenvector? So if that v is an eigenvector, then the following must be true. So it must be true that the a value, this a, 4, 3, -1, 0, that thing times the eigenvector, the supposed eigenvector, this one right here, 6, -2, that's got to be equal to some lambda times that same 6, -2. In other words, what we're basically saying is a times v, where these are vectors, so I should probably make that nice and bold here. A times v has to be equal to lambda times v. That must be true. So if this thing really is an eigenvector, then this must be true for a specific, there we go, lambda value. Right? So if this is an eigenvector, then we can prove that it's an eigenvector because this must be true. So let's kind of tease this out. So what happens when we multiply those two matrices? Well, we have a 2 by 2 times a 2 by 1, so we're going to wind up with a 2 by 1. And in the top, it's going to be 4 times 6, so that's 24, or plus 3 times -2, so minus 6 on the top. And on the bottom, it's -1 times 6, plus 0 times -2. So that has to be equal to some lambda times 6, -2. Now you'll notice I didn't really do anything over here because the action is really on this side. So with a little bit of simplification, we have a column vector on this side. 24 minus 6 is 18. And this is just -6. And so the question is there a single number, lambda, that I can multiply this thing by to get that? And if you don't see it in terms of a matrix, if you don't see it in terms of a matrix equation, remember that you can always think of this as a pair of equations. The top equation is 18 equals lambda times 6. And the bottom one is -6 equals lambda times -2. Now, is there a lambda that works for both of these? Is there a lambda value that makes both of these true? Well, on the top one, you're like, oh, just divide by 6. Lambda equals 3. Notice down here, if lambda equals 3, it also works. And so from both of these, you wind up with lambda equals 3. And so this is true if lambda equals 3. So v is an eigenvector. And we can say it's associated with lambda equals 3. So we just proved it, because this equation in orange has to be true if something's an eigenvector. So what about this? Now you'll notice it's written horizontally. That's just lazy math teacher or lazy math textbook, right? And so this is really the same thing as the vector 2, 1, right? So if that thing is an eigenvector of A, then we can set up that exact same equation. So it's going to be a times the vector has to equal some lambda times the vector. So then a, which we know from up above is 4, 3, -1, 0, this thing times 2, 1 has to be equal to lambda times 2, 1. Then this must be true for some particular lambda value. Okay, well, let's see if it works. So 4 times 2 is 8, plus 3 times 1, that's 11. And in the bottom, -1 times 2 is -2 plus 0. So on the left-hand side, we have a vector that is 11, -2. On the right-hand side, we have lambda times 2, 1. Is there any lambda value that you can multiply this vector by to get it to look like this? You're like, I don't think so, because lambda times 1, to get -2, it'd have to be -2 down here. But on the top, -2 times 2 does not equal 11. And so, since there's no lambda value that works, we can say that 2, 1 is not an eigenvector of that coefficient matrix A. Right? Wah, wah. So we've seen an example where we prove that it is an eigenvector, and we've seen one where we prove that it isn't. But the key comes down to the equation, and that's a super important equation. It's your coefficient matrix A, whatever that is, times your eigenvector V has to be equal to lambda times your eigenvector V. That equation has to be true in order for it to be an eigenvector-eigenvalue pair. It's the only way it works. So let's put this all together. And on the very last time, we're going to go back to our example from before. And so we're going to put it all together by taking a look at that system one last time. So when we figured out what the lambda values were, we came up with 2 lambda values. And we called this one lambda 1, and we called this one lambda 2. And I'm going to color code them because, as you can imagine, it's kind of important. So lambda 1 was associated with this vector right here. And we called that eigenvector number 1. And lambda 2 was associated with this vector right here. And we call that eigenvector 2. So eigenvalue, eigenvector. Those are like a matched pair. Eigenvalue, eigenvector. They're a matched pair. But wait, because we know for this particular system of differential equations, we happen to know these 2 solutions. Now take a close look at this. Take a close look at writing, and I'm going to write this in a different color so it stands out a little bit. I'm going to rewrite this. We saw that we could factor this. We factored as e to the 2t times the vector 1, 0. See anything familiar? And for y2, the other straight line solution, we saw that we could factor out, I'm going to factor out a negative e to the -4t. And you'll see why in a second by factoring out that negative. I'm left with 1 up here and -2 down here. See anything familiar? You should see this guy right here. That is your eigenvector number 1. But look closely at the rest of it. Do you see that exponent up there? Do you see how it is the exact same thing as lambda 1? This thing right here, that's lambda 1. And guess what? Big surprise. For our second pair of eigenvector eigenvalue, we have our eigenvector number 2 right there, that's what we called V2. And if you look carefully upstairs in the exponential right there, that is eigenvalue number 2. And if you're thinking this is just a really strange coincidence, it is totally not. It is totally not a coincidence. Because if, and this is kind of putting it all together, if we know lambda and v, the eigenvector and eigenvalue, are an eigenvalue/vector pair, then, and this is the big flourish, we know a straight line solution. And the straight line solution format looks like this. E to the lambda times t, there's my eigenvalue upstairs, times the eigenvector v. Just like here or here, the vector. This is a straight line solution for the system. This is huge. We just found a way to go from what's lambda and what's the associated vector to writing the equation of the straight line solution. This is enormous. This is going to help us out tremendously. And because it's so important, it has a theorem associated with it. So on the next page at the top, we're just formulating this in a very formal way. Suppose we have a coefficient matrix A, and it has a real eigenvalue lambda and an associated eigenvector v. Then this thing is a straight line solution. This is guaranteed to be a particular solution. Straight line solution. Moreover, if you know multiple values of lambda and multiple values of v, then you have multiple straight line solutions. So if you have 2 of them and you can put them together, then you can put together your straight line solutions and come up with the general solution. Now you'll notice it's a general solution because we have a constant here and a constant here. And in both cases, it's a constant times a straight line solution. This is SLS number 1. And right here, this is SLS number 2. So we have a straight line solution times a constant. And if you've got 2 of them, then you have the general solution. And we get this by way of that linearity principle that we saw a while ago. And so this is huge. We have a shortcut to get the general solution of a linear system. All we need to know are eigenvalues and eigenvectors. And I don't know if you remember, but finding lambda and finding v required no calculus. And this is huge. We're able to essentially solve a differential equation without doing any calculus. Think about that for a second. Remember, finding lambdas involved, solving a quadratic equation, and finding v's was just manipulating linear equations. It wasn't terribly difficult, and it was stuff that you could do as a pre-calculus in a pre-calculus class. But yet, it's at the heart of a pretty complicated calculus problem. And the good news is that we can actually do this in Maple. So you can find these by hand, certainly, or you can use Maple to find them. And so right down here, you'll notice there's the code that you need. And you need to load a library, which is the linear algebra library. And then you can use linear algebra library to find eigenvectors. And you can do the same thing with eigenvalues. So real quick, I'm going to switch over to Maple, and we're going to try this out. So here we are in Maple. I've already loaded my linear algebra and DE tools just in case we need it. It takes a second for my computer's a little slow today. So we can step down here, and I can ask Maple to find the eigenvalues of a particular matrix. Now I just have to enter what the matrix is, and so I'm going to kind of scoot over here, close down some of this stuff, and I'm going to insert a 2 by 2 matrix. And we'll pick numbers. I'm just going to use the ones that were on the page there. 2, and if you use tab, you hit tab, it just automatically jumps to the next element. So 2, 2, 1, 3. And now if I say eigenvalues this, Maple will say, okay, after a second, because of course my computer's slow. It says, here are your eigenvalues. Now notice it gives them to you, and it kind of looks like they're a vector, but those are really just the two eigenvalues. So we could say lambda 1 equals 4, lambda 2 equals 1. If you want to know the eigenvectors for that same matrix, I'm just going to be lazy and copy and paste here. Notice what Maple gives us. Maple actually gives us the eigenvalues to start with. And it, for some reason, gives it to us in the opposite order. But this eigenvalue is associated with this eigenvector. Now it's vertical, so the 1 here is associated with -2, 1. And the 4 is associated with 1, 1. So I'm just going to flip back over to the document camera so I can write these down. And if you do eigenvectors, you find out that this thing has 2 eigenvalues. Lambda 1, I'll call it 4, and lambda 2, we'll call it 1. By the way, Maple sometimes reverses the order of these things, and I have no idea why. You can have 2 people on 2 different machines doing the exact same code, and they'll get lambda 1 and lambda 2 in reverse order. It doesn't really matter, but it's a little annoying sometimes. So the V1 that was associated with that was 1, 1. And the eigenvector that was associated with this guy, if you remember, was -2, 1. So Maple can do it for us super fast, right? It doesn't take us terribly long to come up with those values, but we can totally find them using Maple. We can double check ourselves at the very least in Maple. And so what we're going to do on the next page is we're going to take a problem from the beginning where we know this coefficient matrix. We're going to find the lambda values. We're going to find the eigenvectors. And we're going to put together our particular straight line solutions and then write our general solution from that. So we're going to kind of take it soup to nuts from the beginning, and that'll be in the next video.